When you hear the word algorithm today, your mind probably jumps straight to digital stuff, right?
Hmm.
Social media, search results, AI maybe.
Yeah, feels very modern, very techy.
But that association, it kind of hides a much deeper story.
Yeah.
The algorithm, the real deal, is way older than silicon chips.
Absolutely. It's foundational.
So for this deep dive, let's try and forget the YouTube recommendations black box for a bit. Our mission is to give you that shortcut past all the tech jargon right into the precise mathematical idea of an algorithm.
Hmm.
We're going to trace its, well, frankly, surprising history, we're talking millennia, and really unpack the powerful recipes, the design methods that make them so good at solving tough problems.
Yeah.
We're hoping for those aha moments, showing why this isn't just code, it's like a pillar of how we think.
Okay, let's start with that core definition, because this is where a lot of the confusion comes in. So formally speaking, an algorithm is a finite sequence of really rigorous mathematical instructions.
Finite sequence.
Okay, yeah, finite. And they're used for computation or solving a specific class of problems. But here's the absolute key. It must produce an output, and it must terminate. It has to provably stop.
Okay. Termination. That's the big divider then, between a true algorithm and something else.
Exactly. That gives us the crucial difference between an algorithm and what we call a heuristic.
Right.
A true algorithm, it seeks an exact, often optimal result, and it has to halt. A heuristic, though, that's more like an approach, a shortcut, maybe a rule of thumb. You use it when finding the single best answer is impossible or just takes way too long.
So back to the social media example. When a platform tunes its feed to keep you scrolling, and everyone calls it the algorithm, our sources say that's actually more heuristic-based because there isn't one single provably right recommendation. It's just trying to guess what keeps you engaged.
Precisely. It's constantly adjusting, optimizing for behavior, not finding a fixed mathematical best. It's, a mechanism for ongoing improvement, not necessarily finding the answer. That formal definition, it sets a really high bar.
Okay, let's dig into the history.
Yeah.
Because the word itself, the etymology, it's just fascinating. Most people probably assume it's Greek, right? Like arithmetic.
Yeah, sounds Greek-ish, but nope. Completely wrong.
So where does it come from?
It's a fantastic trip back to 9th century Baghdad. The word algorismi or algorismi,
Yeah.
it's actually a Latin version of the name of a Persian polymath, Muhammad ibn Musa al-Khwarizmi.
Get out. So the word algorithm is basically someone's name, slightly mangled by history.
Pretty much. Al-Khwarizmi wrote these incredibly important texts on Indian calculation methods. Centuries later, when they got translated into Latin, the translators often started with Dixit algorismi.
Meaning it.
Thus spoke al-Khwarizmi, and the name just sort of stuck to the process itself.
Wow. But the idea of a strict procedure, that's much older than him, right?
Oh, way older. We need to step even further back. The earliest solid evidence, Babylonian math, maybe around 2500 BC, they actually described an early division algorithm on clay tablets.
Seriously. Division.
Yeah, and later, maybe 1800 to 1600 BC, they had procedures, algorithms for calculating complex formulas they used for astronomy.
Okay, so Babylonians. Who else?
Well, it pops up elsewhere, too. Ancient Egypt, the Rhine Mathematical Papyrus, that's around 1550 BC, has arithmetic procedures. Then the Greeks, of course, really formalized things. Think Euclid's Elements, around 300 BC, contains the famous Euclidean algorithm.
For finding the greatest common divisor. Yeah, I remember that one.
Right. And what's really cool is people were applying this structured thinking even without machines. Like Al-Kindi, another brilliant Arab mathematician from the 9th century.
What did he do?
He developed the first known cryptographic algorithm, a step-by-step method for breaking codes using frequency analysis, a true algorithm centuries before computers.
That's incredible. Okay, fast forward a bit. Mechanical devices start appearing. With the connection there. Our sources mention something surprising. Clocks.
Yeah, it sounds odd, doesn't it? But some historians argue the weight-driven clock, specifically the verge escapement mechanism inside it, that was maybe the key invention that paved the way for computing machines.
How so?
Well, it was the first really accurate automatic machine. It showed you could control complex motion precisely over time. And that idea led to mechanical puppets, automata, and eventually people like Babbage started thinking about mechanical calculation.
Which brings us neatly to Ada Lovelace, often called history's first programmer.
Exactly. She saw the potential in Charles Babbage's analytical engine. She realized it wasn't just a calculator, it could be programmed. It was arguably the first design for a real general-purpose Turing-complete computer.
And she wrote the programs, or algorithms.
She designed the first algorithm specifically intended for that machine. She really bridged that ancient idea of a rigorous procedure with the potential of a formal mechanical system. A huge leap.
So the concept was there, percolating for centuries. But the heavy-duty math needed for modern computing, that came much later, right, in the 20th century, and it was sparked by some kind of crisis.
That's right. The modern formalization really kicked off around 1928. It was driven by attempts to solve something called the Entscheidungsproblem.
The decision problem,
Yeah.
posed by David Hilbert.
Yeah. Hilbert essentially asked, is there a definite mechanical procedure, an algorithm, that can determine if any given mathematical statement is provable? A huge question about the limits of math itself.
And trying to answer that gave us
The foundations. Alonzo Church developed lambda calculus, and Alan Turing came up with his Turing machines, both around the mid-1930s. They provided formal models of computation.
the Turing machine. That sounds important.
It's incredibly elegant. Turing showed that you only need a tiny set of basic instructions to perform any possible computation. You need, let's see, conditional jumps, like IFGOTO, unconditional jumps, GOTO, assignment, storing a value, and a HLT instruction.
That's it. Just those 4 things can run any algorithm.
Fundamentally, yes, that's what Turing completeness means. It's the theoretical minimum for universal computation.
Okay. And we don't always need code to write these things down.
Right.
There are other ways to represent them.
Definitely. You can use natural language, though that can be ambiguous. More often, for thinking and analysis, people use pseudocode. It's like simplified programming language mixed with English.
Easier to read than actual code.
Much easier, usually.
Yep.
And flowcharts, very visual. They use standard shapes. Rectangles for simple steps, diamonds for decisions.
The if-then else points.
Right. And arrows showing the flow. It forces you to be structured, clear about the sequence and the choices.
Let's make this concrete. Simple task. Find the biggest number in a list. How would that look formally versus informally?
Informally. You just say, look through the list, keep track of the biggest one you've seen so far. Easy.
But the quasi-formal pseudocode.
That demands precision. You'd use symbols, like the arrow I for assignment. You'd explicitly say, step 1, set a variable, say largest, to the value of the first item in the list, like largest at L0. Then you loop, compare, update. Every step is unambiguous. That's the algorithmic rigor.
And that rigor allows us to actually analyze them properly, which brings us to algorithmic analysis.
Exactly. Once it's formally defined, you can measure it.
Why should someone listening, maybe not a coder, care deeply about analyzing algorithms?
Because it's all about cost. How much time will it take? How much memory or storage will it use? Especially as the amount of data, the input size, which we usually call N, gets bigger.
Right. Performance matters. And that's where big O notation comes in.
That's the standard language for it. Big O describes how the time or space requirement grows as N grows.
Okay, refresh my memory. What does something like ON actually mean in plain English?
ON means linear growth. If your input list N doubles, the time roughly doubles. Like adding up all the numbers in a list, you have to look at each of the N numbers once.
Simple enough.
But the space needed for that sum could be O1, constant space, if you just need to store the running total. You're not storing the whole list again.
Got it. But the real magic happens when you compare different approaches, right? You mentioned binary search earlier for searching a sorted list. Why is that so much better than just checking one by one?
Ah, that's the power of efficiency. Checking one by one. That's sequential search. That's OON. In the worst case, you check everything. Binary search, though, is O log n, logarithmic time.
Logarithmic, meaning?
Meaning every check lets you throw away half the remaining possibilities. Think searching a phone book with a billion names. ON might mean a billion checks. O log n, you find it in about 30 checks.
30 checks versus a billion. That's astronomical.
It's the difference between something being practically instant and something being impossibly slow as data grows. Logarithmic scale is incredibly powerful.
And these aren't just theoretical games. The sources mention real-world impact, like with FFT algorithms, fast Fourier transforms, used in image processing.
Oh yeah, huge impact. Recent innovations in FFT algorithms, which are critical for things like MRI and CT scans, have achieved incredible speedups.
How much?
Up to 1,000 times faster processing in some cases. Think about what that means for patients' faster diagnoses, or for portable devices processing complex medical images on the spot with way less battery power. That's not just a small tweak. It enables entirely new possibilities.
Wow. Okay, before we get into how these algorithms are designed, you mentioned performance boundaries.
Right.
Best and worst case.
Right. You need to understand the range. Best case, the input that makes the algorithm run fastest, like finding the item you're searching for on the very first try.
And worst case.
The input that makes it take the absolute longest, use the most resources. Often that's searching for something that isn't even there, forcing it to check everything. For reliability, analyzing the worst case is usually the most critical thing. You need to know the upper limit.
Okay, history, analysis, boundaries.
Yeah.
Now let's talk about the design strategies, the recipes programmers use.
Yeah, the design paradigms. These are general approaches to building algorithms. One of the most fundamental is divide and conquer.
Break it down, solve the pieces, put it back together.
Essentially, yes. You repeatedly break a problem into smaller, similar subproblems, often recursively, until they become simple enough to solve directly. Then you combine the results.
And the classic example is merge sort.
Merge sort is perfect. Take a jumbled list, split it, sort the halves recursively, then merge the two sorted halves back together. Binary search is actually a simpler variant called prune and search. You solve one smaller piece but don't need to combine anything.
Okay, divide and conquer. What's next?
Dynamic programming. This one sounds complicated, but the idea is powerful. You use it when a problem has two key properties: optimal substructure and overlapping subproblem.
Oh, okay. Let's unpack those. Overlapping subproblems. How's that different from divide and conquer? Don't they both use subproblems?
They do, but here's the key. In dynamic programming, the same small subproblem often needs to be solved over and over again as part of solving different larger problems. Divide and conquer typically doesn't resolve the exact same subproblem multiple times.
Ah, so it's inefficient if you keep recalculating the same thing.
Hugely inefficient. So dynamic programming uses a trick called memoization, which is really just a fancy word for caching results.
Smart caching. You solve a piece once, store the answer, and if you ever need it again, you just look it up instead of redoing the work.
Exactly. It avoids redundant computation. And this caching can sometimes take problems that would otherwise have exponential complexity, basically impossible for large inputs, and bring them down to polynomial time much, much faster. The Floyd-Warshall algorithm for shortest paths in a graph is a great example.
Incredible difference. Okay, what about approaches focused purely on optimization? Finding the best solution.
Right. One approach is the greedy method.
Sounds impulsive.
It kind of is. Greedy algorithms build up a solution piece by piece, always making the choice that looks best right now, at the current step, without looking ahead too far.
Make the best local choice and hope it leads to a good overall result.
Pretty much. The downside is they can get stuck in local optima. They find a good solution, maybe the best one in the immediate vicinity, but not necessarily the overall best possible solution for the whole problem.
Like only looking one move ahead in chess. Might look good now, but could be a trap later.
Exactly. Kruskal's and Prim's algorithms for finding minimum spanning trees in graphs. Those are classic greedy algorithms. They work well for that specific problem.
Okay, so if greedy might get stuck, and sometimes the absolute best is too hard to find, what else is there?
Then we often turn to heuristic methods for optimization. This circles back to our earlier distinction.
Right. Heuristics aren't guaranteed to be optimal, but they aim for good enough.
Precisely. When finding the exact best solution is just computationally infeasible, maybe the search space is unimaginably huge, heuristics find solutions that are close to optimal. They often use clever trial and error techniques, like simulated annealing or genetic algorithms, trying to gradually improve the solution.
So a whole toolkit of approaches depending on the problem. It's amazing how these abstract logical recipes, going back thousands of years, end up running everything.
Yeah.
But what about their status in the real world, like legally? Can you patent an algorithm?
That's a tricky area. Generally speaking, in the US at least, algorithms by themselves, just the abstract mathematical steps, are not patentable. They're considered abstract ideas like laws of nature.
There's always a but.
The but is if you apply that algorithm to a specific practical application, if it's an integral part of a tangible process or machine.
So the math idea alone isn't patentable, but using it to do something concrete might be.
Exactly. The famous case is Diamond v. Dyer. The Supreme Court ruled that an algorithm used to help cure synthetic rubber more effectively was patentable because it was tied directly to a physical industrial process. The application made it patentable, not the algorithm in isolation.
Okay, that makes sense.
Yeah.
So this whole journey, it's taken us from, what, Babylonian clay tablets all the way to the formal logic of Turing and modern computers.
Yeah, quite a span.
We've seen an algorithm as this rigorous, finite, terminating sequence. We've learned how to measure its cost with big O. And we've explored these core design patterns, divide and conquer, dynamic programming, greedy methods.
Understanding these recipes really gives you a powerful mental toolkit for thinking about problem solving in general, way beyond just coding. It's about structured thinking.
We've definitely moved past just thinking about social media feeds. This is the bedrock of computational logic. Okay, so let's leave our listeners with a final thought to chew on. Despite all these incredible speedups, we talked about the 1000x gains, the cleverness of dynamic programming, the power of running things in parallel on modern chips.
Yes.
Our sources mention that some problems seem to be inherently serial.
That's a fascinating and somewhat sobering point. It means there are problems out there that fundamentally just cannot be broken down and solved faster by throwing more processors at them in parallel.
They have no parallel algorithm. You just have to do step 1, then step 2, then step 3. No shortcuts.
Essentially, yes. Their very nature demands a sequential approach. No matter how much computing power you have, the logic itself forces you down a single path, one step at a time.
So the final thought is this. If some fundamental problems resist being parallelized, what does that mean for the ultimate limits of computation? Are there questions, maybe some of the biggest questions, where we're just destined to wait, step by painstaking step, for an answer, simply because the logic itself forbids a faster way?
It suggests there might be inherent speed limits built into the fabric of certain problems, regardless of our technology. Something profound to consider.
Definitely something to think about.
Yeah.
We'll leave it there for this deep dive.